Hello again. It's time to talk statistics. So, where are we? Well, this is Stat 374, and we've been talking about the binomial distribution, the binomial probability distribution, which we symbolize with a B. Some people use uppercase, some people use lowercase, and an N for the number of independent repeated trials, and a P for the probability of success on any individual trial. And if a probability distribution is binomial NP, then we can calculate any probabilities associated with that distribution that we need. And this is a probability distribution that comes up a lot in day-to-day computation. You need the binomial distribution. So as an example, I just fiddled with this over the weekend. I looked at a website called, let's see, what was it called? Worldometers.com. And it's a site that has a lot of statistics. But among other things, it had the statistic that the Texas active cases, that was COVID-19, Texas active COVID-19 cases was 169,708. Now this was on 3, and it must have been about 3/5/21. Now I looked up a definition of active cases, and active cases is everyone that has been diagnosed with COVID-19 minus those that have recovered minus those that have died. And so this would be those that we know about that are currently battling with COVID-19. Some would be in the hospital, of course, and some would be doing self-isolation, and some would be flaunting what's good for the public health and just going out and mixing and mingling. So that's the active cases in Texas. Now the population in Texas at about this moment is 29.4 times 10 to the 6 people. And this, of course, would be people also. So using the classical definition of probability, if we just select a person at random, the probability that they carry COVID-19, I mean, this is an active case, so regardless of how well or sick they are, they would be shedding the virus. So the probability, and that's what I mean by carrying COVID, I mean they can share that virus with you. This probability would be equal to 169,708 divided by 29.4 times 10 to the 6 would be equal to 0.00577. So I guess maybe you want to say not all that much of a chance that you're going to bump into somebody that has COVID-19. That would be the probability that a person that you randomly selected from the population of Texas would be positive for COVID-19 and presumably shedding the virus. Well, then I want to ask this question. If we join a group of N persons what's the probability that one or more of the N are shedding virus. So that's a pretty straightforward question. We join a group of N persons, and so after we join there are N plus 1, but we'll assume we know that we're negative, and so we're just really concerning ourselves with the group that we join, the N persons that we join. What's the probability that one or more of these people are shedding virus? So let's let X equal the number in the group of N that are shedding. Then the question we just asked is, what's the probability that X is greater than or equal to 1? That is the question. Now, that would be equal to 1 or equal to 2 or equal to 3. So all in all, I think the probability that X is greater than or equal to 1 is going to be easier to compute if I use the law of complements and say that's 1 minus the probability that X is. Now, we have to find the complement of greater than or equal to 1. Well, that would be less than 1. Now, recall that X is a discrete random variable. It's not going to take on values of a half or a third. If it's less than 1, the biggest it could be would be 0. So this would actually be 1 minus the probability that X is equal to 0. Now, at this point, I think we might as well just look and see what kind of a random variable is. So X is defined on N repeated trials. The N repeated trials would be the N people. You look at the first one, they're positive or they're not. You look at the second one, they're positive or they're not. You look at the third one, they're positive or they're not. And so X is defined on N repeated trials. There are two outcomes, and that would be success or failure. Positive for COVID-19, negative for COVID-19. And X counts number of positives. Well, it's not much of a stretch to think about these N repeated trials as being independent. Now, of course, there's some debate there, but overall, I think we'd be justified in saying that if we've randomly selected the group, if we join a group that's not assembled because they're all brothers and sisters or because they all live in the same house, but just kind of a random grouping, it's not much of a stretch to say that these N trials would be actually independent. Two outcomes, X counts the number of positives, then X would have a probability distribution that would be binomial, and N, and the P, the probability of being positive, would be 0.0577. Well and good so far. But the reason we went through that, I mean, first of all, because we're studying a chapter on the binomial distribution, so I wanted you to see that it pops up in life on a regular basis. The second is that we know how to calculate this probability that we're asking for, all of these probabilities, in fact, since we know the distribution of X. If we know the distribution of a random variable, we can calculate every probability we need. If we don't know the distribution, we can't calculate any probabilities. And so that's why we're putting some emphasis on defining distributions of random variables and practicing being able to recognize them. So since we know the distribution of X, what's the probability that X is equal to 0? Well, we would know how to look that up with Minitab, but let's do this one by hand just for the heck of it. Now, the probability that x is equal to 0, using the probability function that I've defined for you in a previous video, or that you can find in your book, would be n choose, now this is a probability x is equal to 0, so it would be n choose 0, p, which would be 0.00577 to the 0, and then q would be 1 minus p, and so q would be 0.99423, and that would have to be raised to the power n. Now, we still haven't really said what n is, and so we're going to get a symbolic answer here, but we can take this a bit further. N choose 0, if you've got n things, how many ways can you take none of them? Well, there's only one way to do that. Don't take any. N choose 0 by common sense would be 1, or if you work it out with factorials, it will also turn out to be 1. So n choose 0, this coefficient is 1. What about p to the power 0? Well, any number raised to the power 0 is 1. So far we've got 1 times 1. And then we finish up here with 99423 to the power n. Now that's the probability that x is equal to 0. But what was the question we asked? We said, what's the probability that you're going to be rubbing shoulders with one or more people that are shedding a COVID virus, that is x greater than or equal to 1. And we calculated that was going to be 1 minus the probability that x is equal to 0. So this would be 1 minus, and the probability that x is equal to 0 is 0.99423 to the power n. And so at least up to the n, the crowd size, we've calculated the probability that if you go out in a crowd, you're going to be rubbing up against somebody that is shedding coronavirus. Now, how big would that crowd have to be? How large in before the probability is significant? What do we mean by significant? Let's just agree, and this is an agreement we've made before, that the probability that we're contacting somebody that is coronavirus positive is greater than or equal to 0.05. We said less than 0.05 is nothing to worry about. You know, we've said that that is not a thing we're going to get excited about. The 0.5 we imposed ourselves. We kind of made it a cutoff between likely and unlikely. So being exposed to one or more COVID people would be likely if its probability was more than 0.5, unlikely otherwise. Instead of using likely and unlikely, this time I've used significant. They would mean the same thing. Well, I think now we can probably answer the final question, that is, how big would n be before this probability became significant? And so we would want to know for what n is 1 minus 0.99423 to the power n greater than 0.05. So there's the question. Now, we can just solve this with algebra that we know. Let's transpose the 1 to the right-hand side. So negative 0.99423 to the power n would be greater than, now this would be 0.5, and when I transpose this, it would be minus 1. So this would be 0.95 with a negative sign in front of it, negative 0.95. Now, probably the next thing that we'd want to do would be to make this positive on both sides. So I'm going to multiply left and right by -1. And when I do that, I get 9, 9, 4, 2, 3 to the n over here. And I get 9, 5 on the right-hand side. But when I multiply by a negative value, I've got to reverse the inequality. So it looks like that. Now the next step, since we want to solve for n, the thing in the exponent position, you know from previous work you have had in algebra, prerequisite for this course, that we would take the logarithms. So I would use the natural logarithms and say 9, 9, 4, 2, 3. Now a law of logarithms is that the log of this number to the n is the same as n times the log of the number. So that, of course, is why when you've got to solve for an exponent, you use logarithms. So that would be less than, now if you take the log on the left, you've got to take the log on the right also, 0.95. And we're almost done. Now we divide by this coefficient, left and right, and we would have an n on the left-hand side. Now, if I divide by a negative quantity, I've got to reverse the inequality. It's going to have to flip back over because the log of this value is going to be negative. The log of anything less than 1 is going to be negative. So I'm dividing left and right by the log of 0.99. That's going to be a negative value. So I'm going to get n greater than natural log 0.95, and then what I'm dividing by is the natural log of 0.99, that's a parentheses, not a 1, 4, 2, 3, and that's equal to 8.818. 8.818. So what is that telling me? If I join a crowd that's greater than 8.818 people, so what would that have to be? Be greater than 8, greater than 9, greater than or equal to 9 people. So let's, for emphasis, I guess I'll change color and say, therefore, if n is greater than or equal to 9, the probability of x greater than or equal to 1 is greater than 0.05. That is, there's a significant probability, and you can try this with different values for this probability. When does it reach 50%? Well, you can work those out just with minor modifications to this problem. I see that we spent going on 19 minutes with this problem, so I think that's appropriate, but that's enough for this video. So thank you for watching. You have a good afternoon or evening or morning, depending on where you are and what you're doing. Goodbye.